Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on discrete dynamical systems. So to illustrate what this is all about, I found a really good example in David Lay's book Linear Algebra from 2006, so I'll go through that. So this example involves calculating the vector xk, which is the population of owls at time k and the population of rats at time k. This is a predator-prey model. The owls prey on the rats, and so the populations of each are linked to the other. So let's say the equations linking them are given as follows. So note that in these equations, k refers to the number of months. So because we're recalculating their populations after each month, not continuously, this is a discrete system. So the first equation is saying that the population of owls next month is 0.5 the population this month. So that's saying that 50% of owls will survive to next month if there are no rats for food. And then this term here is saying what will happen if food is plentiful. Enough rats, then most of the owls will survive and the population may even grow their producing offspring. For the second equation, I apologize, this term should be negative. So this is talking about the owls preying on the rats. So this is the population that will die due to predation by the owls. And then this term here says that if there were no owls, the rat population would grow by 10% each month. So what we want to do is look at the long-term population of both the owls and the rats. So we're going to put all of this information into a matrix. So what will happen is we have our matrix and we're going to have some initial vector x0. So I'm going to call it O0 and R0, the population of owls and rats to begin with. So after 1 month, I can find the population by just applying A to x0. And after 2 months, I can just apply A to x1. But that would be A times x0, which is A squared, x0. So hopefully you'll understand there's a pattern. The time k, the population will be given by A to the power of k times by x0. So we're interested in what this will equal as k gets larger and larger, approaches infinity. So we're going to digress to discuss the theory behind figuring out what that would be. So we're going to be calculating high powers of A. So that takes a lot of operations with a computer and is virtually impossible by hand. We want to find a simpler way of doing things, and it turns out that involves eigenvectors. So what do they have to do with this? Well, it'd be helpful if we were using eigenvectors, because if V is an eigenvector of A, so remember eigenvectors are non-zero, then I know that A to the power of k times V, I can just raise lambda, the eigenvalue to that power, and times it by V. So, of course, lambda to the power of k is easy to do because lambda is a scalar. Raising a scalar to a power is easy, and you just times that by the eigenvector. So that's a very easy calculation. The problem, unfortunately, is that x0 will almost never be an eigenvector of A. But what we're going to do is write it in terms of the eigenvectors of A. So I'm going to explain how this works for 2x2 matrices, but everything I say works equally well for 3x3, 4x4 matrices, and so on. We want A to be square. Now we want it to be diagonalizable because that will ensure that the eigenvectors of A are linearly independent. So if A is 2x2 and diagonalizable, let's say its eigenvectors are V1 and V2. If they are linearly independent, that means I will always be able to write x0, whatever it is, in terms of them as something times the first eigenvector plus something times the second eigenvector. So if I want to apply A to the power of k to this vector, I do it as follows. So because of the distributive law for matrices, I can just expand the brackets as normal. So I can write C1 and C2 first in their respective terms. Remember, C1 and C2 are just scalars, V1 and V2 are vectors, A is a square matrix. Because of what we wrote up here, we can rewrite this part of the first term and this part of the second term. I get C1 equals, so lambda 1 is just the eigenvalue associated with the first eigenvector, and similarly lambda 2 associated with the second eigenvector. So we now have this expression here. It may look a little more complicated, but it's going to be really easy to see what will happen as k approaches infinity. So the first statement in red says that if every eigenvalue is greater than 1 in absolute value, then 0, 0, the origin is a repeller. So what would happen is if this here, if lambda 1 is greater than 1, lambda 1 to the power of k gets larger and larger as k approaches infinity. Similar for this here. Because they get larger and larger, the whole thing gets larger and larger. It moves away from the origin. The vector a to the power of k x0 gets larger and larger. It approaches infinity. That's why we call 0, 0 the origin a repeller. So it turns out if all of the eigenvalues are less than 1 in absolute value, so that means as k gets larger, this will approach 0, this will approach 0, so the whole thing will approach 0, will approach the origin, and so we say the origin is an attractor. Okay, so what would happen if we had some eigenvalues greater than 1 and some less than 1? Well, again, I'm just looking at the 2 by 2 case, but this will work equally well for higher dimensions as well. So let's say in our one here that lambda 1 is greater than 1 and lambda 2 is less than 1. So what we would expect is that because this one approaches infinity, doesn't matter that this one's less than 1, the whole thing will just get larger and larger. Well, that is usually the case. There's just one exception, and the exception is if C1 is equal to 0. If C1 is equal to 0, that means that V2 is x0, or x0 is an eigenvector of A corresponding to an eigenvalue that's less than 1. And if that's the case, then the whole thing would actually approach 0. So it approaches infinity as long as C1 is not equal to 0, but if C1 is equal to 0, then the whole thing will approach 0. So this means that if A has some eigenvalues more than 1 and some less than 1, it will almost always approach infinity, get larger and larger, unless the initial vector is an eigenvector corresponding to an eigenvalue less than 1. Now, for the case where the largest eigenvalue is equal to 1 in absolute value, it turns out it will approach a steady state vector, and we're actually going to look more at that in Markov chains next time. So what does this mean in terms of population? So it means for our matrix A that regardless of the initial vector, the initial population, if the eigenvalues are more than 1, the population of both rats and owls will get larger and larger. It means that if the eigenvalues of A are both less than 1, then both of them will eventually die out. Their populations will get smaller and smaller. And something weird will happen if one of the eigenvalues is more than 1 and one is less than 1. It means the population will probably grow and grow unless the initial vector is an eigenvector of A, then they may die out as well. So let's return to our example on the previous slide. So A is written as this. Now we can go through and calculate the eigenvalues as normal using the characteristic polynomial. Again, because we've done it so many times, I won't bore you with the calculation. We get one of the eigenvalues is 1.02 and the other one is 0.58. So this means we can write for this example, xk is equal to some constant times the eigenvalue to the power of k times v1 plus some constant times 0.58 to the power of k times v2. So as k approaches infinity, what's going to happen? This here will get to 0 pretty fast. And then we'll just be left with xk is equal to c1 times 1.02k times v1. So I guess I should say that's approximately equal, because this won't equal 0. It will just get close to 0 very quickly, closer and closer to 0. Now it turns out that the eigenvector associated with the eigenvalue 1.02 is 10, 13. So this C1 doesn't really matter that much. We don't really need to find it in this. What we know is that in the long run, the population of both owls and rats is going to grow, and this says about 2% per month. So this eigenvector tells us the ratio. It's about 10 owls for every 13 rats. Although usually what we do here is we put the number of rats in thousands. So really, this 13 could refer to like 13,000 rats. So RK is in thousands and OK is just in units. So that would mean there are 10 owls for every 13,000 rats. And that's really all there is to it. Once again, eigenvalues and eigenvectors to the rescue. All right, thank you so much for watching this video. This has been the luckiest maths teacher in the world. Have a great day.